Hello everyone, my name is Joyji. I am attempting to explain the Monty Hall problem today. It is one of the most perplexing problems in probability, and since this is my first YouTube video, I would appreciate if you do share this video if you like the content of it. The Monty Hall problem came from a game show. The participants in that game show were essentially given 3 doors to choose from, and behind one of the doors they would typically find a car, and the other 2 doors would have goats. Now once the participant made a choice, let's say in this case door number 1, the game show host, who was fully aware of what's behind the 3 doors, would open another door, let's say in this case door number 3, and then ask the participants whether they should switch. Remember, door number 3 would have a goat behind it. So now the question is whether the participants should switch. And what the answer that we'll try to provide today is whether there's any advantage of switching and what's the probability gain. The way we will try to attempt to answer that question is by invoking 2 concepts in probability and math. The first one is the state space model. The second one is Bayes theorem. For those of you who don't know what a state space model is, here's the Wikipedia definition. It's a mathematical representation of a dynamic system which changes its internal state over time. Here, in this particular case, we will try to measure the internal state in terms of probability, and the way we will do that is by using Bayes theorem. A quick recap on Bayes theorem. Bayes theorem is a probabilistic expression of any event A given a condition B. It starts with the prior probability of event A, and as the condition matures, it adjusts the probability. The mathematical representation of Bayes theorem is given below. It starts off with 2 equations. Both are conditional probabilities, and they are expressed in the form of A given B and B given A. Once you transform these 2 equations, you get equation 3, which is essentially an explicit expression of the conditional probabilities equating the intersection of A and B, and then rewriting that equation you get Bayes theorem, which is probability of B given A is equal to probability of B multiplied with probability of A given B, and the entire numerator divided by probability of A. That said, and that clearing the concepts that we need to know, let's move on. So the construct, as discussed earlier, is there are 3 doors, and as a participant, let's say you choose any one of the 3 doors. The probabilities initially of finding a car behind any one of the 3 doors is equal, and it is expressed as 1 upon 3, which is 0.33. Similarly, the probability of the game show host eliminating any one of the 3 doors is expressed in the form of P of D1, D2 and D3 respectively. Now, let's dwell deeper. As you choose door number 1 as a participant, you set the initial state. So the initial state is chosen, which is door number 1. Now, the game show host has to now intervene, and the game show host now has to open either door 2 or door 3. Remember, the game show host cannot open door 1 because that would mean a preemptive end to the game. Now, the game show host also needs to be considerate of the fact that they cannot open the door which has the car behind it, because that again will lead to a preemptive end. So, in this case, the game show host decides to open door number 3. Now, the probability of the game show host opening door number 3 is expressed in the form of the equation that you see at the right hand side. So now, if you look at the equation on the right hand side, which is the game show host's probability of opening door 3, it is actually expressed in the form of 3 conditional probabilities, where the probability of opening door 3 is considered against where the car is available, whether it is available behind door 1, door 2 or door 3. So it is expressed in the form of P of D3 given C1. Here C1 stands for the car being available behind door 1. And likewise P of D3 given C2, where C2 stands for the car being available behind door 2, and P of D3 given C3, here C3 stands for the car being available behind door 3. If you further look to the right, you will see that the expression can be broken down into their individual probabilities, and these probabilities are 0.5, 1 and 0. Now let's understand why is it 0.5, 1 and 0. In the first case, where the car is actually behind door 1, the game show host has an equal probability of opening door 2 or door 3, and hence the probability is 0.5. In the second case, when the car is behind door 2 and given that the participant has chosen door 1, the game show host is constrained and has to open door 3, and hence the probability equates to 1. In the third scenario, where the car is behind door 3, the game show host cannot open door 3, and instead they have to open door 2. But given that they have opened door 3, you can safely assume that this condition never occurs. So hence the probability is given as 0. Now, if you add these probabilities in the summation, you will find that the composite probability of P of D3 exceeds 1. It is actually 1.5. But there's a problem here. The problem is we haven't factored the probability of finding the car behind either door 1 or door 2 or door 3. Now if you rationalize this equation further with the individual probabilities of finding the car behind any one of these 3 doors, which is expressed here in this expression at the bottom, you will see that there's a rationalizing factor which is 0.33, which comes into the equation, and when you multiply that across each of these 3 conditional probabilities equally, you get a value for P of D3 which is equal to 0.495, or roughly half. Now that we've established the probability of the game show host opening door 3, let's move to the second state of transformation here, which is the participant choosing to either stick with their original option of door 1 or switching to door 2. Now, for us to establish whether the participant should switch or stick to their original option, we will have to calculate 2 conditional probabilities, and these 2 conditional probabilities are P of C1, which is probability of finding a car behind door 1 given that the third door is opened by the game show host, and likewise the probability of finding a car behind door 2 given that the game show host has opened door 3. Now remember, this is a state space model, and hence each of these probabilities are maturing over time, and hence we are looking at it through the prism of conditional probability, where every event is sequential. Now let's see how these individual probabilities shape up. So if we now apply Bayes theorem to the first condition, which is probability of finding a car behind door 1 given door 3 is opened, the expression is at the lower left bottom corner. And similarly, the same Bayes expression is given in the right bottom corner. Now, if you look closely at the expanded forms of these probabilities, you will see that each of the components of the conditional probabilities have already been calculated. Say for example, on the left hand side, we already know what is probability of finding the car behind door 1, which is P of C1. We already know what is the probability of finding of opening door 3 given that the car is behind door 1, and likewise we know the probability of opening door 3 in general. Similarly, on the right hand side, we know what is P of C2, we know what is probability of D3 given C2, and what is the probability of D3 in general. When you plug these values from here into this equation, you see that the probability on the left hand side, which is the probability of sticking with the original option in case the participant decides to do that, is actually 0.33, and on the right hand side the probability of switching is actually 0.67. so there is definitely a gain in probability if you switch. So as a participant, if you are in this kind of a scenario, you should always switch. Now finally, the question is, why is there a gain in probability for switching, while if you stick to your original options there is no gain? Now the reason there is a gain in probability for switching is primarily because it is a state space model and its internal states change over time. Here the internal states are conditional probabilities, or the probability of finding a car behind the door that you're choosing updates and changes over time as the game show host intervenes and changes the system, and hence it is always wise to switch. So that's it, and I hope this explains the Monty Hall problem and why you should switch always as an option. If you feel like, do share the video with your friends, and I will hopefully be back with a few more interesting topics in the future. Thank you.